like that beginning part in, I think we're doing an exam review session in forum rules. Everybody's like, you want to come out and drink with us? I'm like, yeah, I'm going to say that on the recording that I'm posting on YouTube. Great. It's like, thanks, everybody. I know what you all were doing. You're trying to get me in trouble and whatnot. So, I see how it is. All right, let's get started. Lecture 3. So, I don't know, did anybody have a chance to check out the recording on Lecture 2? I think the audio is fixed, or at least it's a lot better than last time. Let me know if there are any other audio issues, but it's uploaded. It's on the YouTube playlist. The link for that playlist is on the Blackboard course shell, so that way, instead of having 30 or 40 different links, there's just one link right there on Blackboard. I'm going to wait until after 5 p.m. and whatnot to upload attendance grades by Monday. That'll get taken care of. Homework 1 was due today. That was pretty easy, right? Hopefully, that was pretty straightforward. Good. Okay, so homework 2.1 is assigned today. That's due on Monday. And I would say that starting today, we actually start getting into it. We really start getting into structural analysis. The last lecture that we did was really, it was our classification lecture where we can take a structure and assess whether or not it is statically determinate, statically indeterminate, whether it's stable or not, etc. What we're now going to be doing is actually some structural analysis. Now, we start off with external support reactions. So we're going to have a few lectures on support reactions. Now, we've done this type of stuff before in statics and whatnot, but we're really going to hit the ground running with this stuff. We're going to start off simple, and next thing you know, we're going to have incline loads and moments and internal hinges and all sorts of crazy stuff. So it's going to get real quick, okay? Now, what we're going to be focusing on for the next few lectures are determining these, the unknown support reactions that keep a structure in equilibrium. Now, to be clear, what we're going to be doing for this module, and really for the next few modules in this class, is dealing with structures with an IE of 0. In other words, these structures are stable and statically determinate. Okay? Now, why is that? Well, number one, we certainly aren't going to be analyzing any unstable structures, because I don't know about you, I really don't want to be building any unstable structures. As for indeterminate analysis, we can do that, but you can't perform indeterminate analysis without the tools that you develop for determinate analysis. So we got to do determinate analysis first. So this is what we're going to be dealing with over the next few lectures, is determining these unknown support reactions. So remember, pin supports have 2, rollers have 1, and fixed have 3 supports. Today, we're only going to focus on pinned and roller supports. We have, I think, reactions 3 is we're going to focus on these. These, I'll argue, these are actually some of the easiest to deal with. That seems counterintuitive because there's more reactions, but cantilever beams are actually pretty easy to analyze because the statics is pretty easy to deal with. So we're going to start off with some pretty basic problems, and we're going to ratchet it up in complexity. So the first problem we're going to deal with is this one right here. Let me pull it up in the notebook so that I have this laid out here. Okay, so here's the problem that we're going to deal with. Let me take this and make it a little bigger. We're going to take this beam and we're going to compute its support reactions. This is about the most fundamentally basic problem that we can do in here, but this will, I guess, shake the rust off, as it were, on your static skills and whatnot. So I have a beam that is simply supported. There's some new terminology that we brought up. So simply supported structures are ones that have a pin support and a roller support. And basically what we mean when we look at simply supported structures is we're looking at supports that do not resist moments. So we only have force reactions on either of these supports. And the idea is that we need to determine the support reactions in order to maintain equilibrium. Now, what we're going to do here is, first thing I'm going to do is I'm going to draw out the unknown support reactions. You've probably done this before, it's just been a little while. So the first thing that we'll do is, let's look at this roller over here on the right. So it's going to have a vertical reaction, and I'm going to call that By, okay? And you notice I've drawn that upwards, okay? Now, I've drawn it upwards because I'm going to have a vertical reaction over here, AY. I'm going to draw that one upwards as well. I think it's common sense, as it were, that I have a bunch of force acting downward on the beam, so the reactions have to push upward to keep it in equilibrium. I think that's common sense. It is going going to happen invariably that we are going to have reactions where they are not going to act upwards. You're going to have reactions acting downward. You're going to be making guesses, and they're going to be wrong, and so on and so forth. What I am doing here by drawing these arrows upward is that I am making an assumption that they act upward. And that assumption will be borne out by the math that I do later. If I assume that these reactions are upward and I get a positive answer, it means that assumption is correct, and they are in fact acting upward. If I assume that they are acting upwards and I get a negative answer, it doesn't mean I need to develop significant emotional distress. It just means that my assumption was wrong and they're acting in the opposite direction. And that is going to happen throughout this semester. And that probably wouldn't have been a big concern for some of the problems we were dealing with in statics or 216, but in here, that definitely can happen. Now, I'm missing a reaction. I'm missing a horizontal reaction here at A. So I'll draw this like this. I think we already know probably what AX is going to be, but again, later, not the case. We're going to have horizontal reactions that we need to deal with. Okay, so now what we're going to do is we're going to solve for our support reactions, and I want you all to stop me if for some reason this stops being familiar or it's been a while since you've looked at this. But we have three equations of equilibrium. We have our sum of forces in the x direction, the sum of forces in the y direction, and the sum of moments. Doesn't this all be equal to 0? And what we're going to do is we're going to utilize each one of these one by one. Now, I'm going to start by dealing with the simple one. Which one's the simple one? AX, right? So if I sum forces, and I'm going to be pretty loose with my format here. If I sum forces in the x direction, what is that going to tell me? It's going to tell me AX is 0. There's no force acting to the left or right. That should be pretty familiar, right? Now, in terms of the vertical reactions, we got two unknown reactions. If I were to go ahead and employ sum of forces in the y direction, I find myself having a little bit of a problem, right? Because I'd have AY and BY going up, but I'd have 20, 30, 18 going down. All I would know is that AY plus BY has to equal whatever this is. So I'd still be left with two unknowns, which is why what I'm going to do first is I'm going to sum moments, okay? Now, typically when you sum moments, what you want to do is sum moments at a location that eliminates as many unknowns as possible. In other words, sum moments at a place where one of your unknown forces pass through that point. So for this problem, I would choose to sum moments at either A or B. For example, if I sum moments at A, I do not need to consider AY because it passes directly through A and generates no moment. Everybody okay with that? Okay, so we're going to sum moments at A. Now I'm going to do this a little differently than what we did in statics. Okay, this is kind of how I like to do it in here. So I'm going to sum moments at A. Now when I say the sum of moments equals 0, what does that mean? That means every moment going this way has to equal every moment that's going this way. So what I like to do is I kind of like to draw a table, and I just put all my moments going like this, put all my moments going like that. We're going to start to have some problems where there's a lot of forces and a lot of components to consider, and I kind of think it's a little easier to just sort of set it up this way. So let's treat this like it's a checklist. So I've got 1, 2, 3, 4, 5, 6 different forces. Let's take care of each one of them one at a time. So let's start off with AX. Do I need to consider AX? No. Even if it didn't go through the point, it's 0. So no. I don't need to consider AY because it goes directly through A. So let's start off with this 20 kips. Does this 20 kips generate a moment at point A? Yes. It generates that moment like this. So it belongs on this left side of the table. Now what's the moment arm? How far is it from A? 6 foot. 6 foot. So what we do is on this side of the table, we write 20 kips times 6 feet. And I assume by now everybody knows what I mean by a kip. A kip is 1,000 pounds. It is a very common abbreviation of forces in civil engineering. You know, we tend to deal with some pretty big loads in our realm. Okay, so you could sort of think of this like a checklist. So I took care of that one, took care of that one, took care of that one. What about the 30 kips? Do I need to consider that? Yes. Which side of the table does it belong on, left or right? Left. And what's the moment arm from A? 15 feet. It's not 9 feet, it's 15 feet because we're summing moments at A, so we need to know how far from A we're at. So this is going to be 30 kips. Times 15 feet. And so what's the next one going to be? It's going to be 18 kips times what?
22.
There we go. This is bringing it back, isn't it? Greatest hits, as it were. Now, is there anything that belongs on the other side of the table? You bet. BY. At a moment arm of 30 feet. So now, you just break out your Casio FX 115 ES Plus or similar scientific calculator or whatever calculation tool you'd like to use. And it's pretty simple. So 20 times 6, that's 120. 30 times 15, that's 450. 18 times 22, I'm not that good. I'm using my cheat sheet here. That's 396. And so you sum those up and you get 966. Although I could be wrong. Do I have a second on that?
Yeah.
Okay, there we go. Yeah, so. Yes, I will do calculations and then ask for a second just to make sure everybody's awake and whatnot. And so that's 966. The units are foot kips or kip feet, whichever one you want to use. But because we've got a kip times a foot, and then that is equal to BY times 30 feet. So we divide both sides by 30 feet. Divide both sides by 30 feet. BY equals what?
32.2.
32.2. And what I do is I usually say that's plus 32.2 because it did come out as a positive number, right? And do I have a second on that?
Yes.
Okay. And so that's plus 32.2 kips. And what that means is because it's positive, I assumed that it was acting upwards, and that assumption was correct. So that's why I say BY equals plus 32.2 kips or 32.2 kips acting upward. Been a while, right? What's that?
Feels like yesterday.
Feels like yesterday. Good. Okay, so now what we got to do is we got to sum forces in the y direction because, you know, if we go to our equations of equilibrium, we utilize that one. We utilize that one. We still got that one to consider, right? So what I'll do is I'll sum forces in the y direction. And I like to do that the same way. I draw myself a little table, and I say everything going up over here has got to equal everything down going over here. And so makes it easy to kind of deal with. So going up, I've got AY and BY, but I know what BY is, so usually what I'll do is I'll say something like, I've got AY going up, and I've got BY going up, but I know that's 32.2 kips. Again, if you have problems reading my handwriting, let me know. I will take it personally, but then I will correct it. That was a joke. All right, so 20 kips, 30 kips. And then 18 kips. And so AY, so over here on the left, AY plus 32.2 kips is 20 and 30 is 50, that's 68 kips. So what's AY?
35.8.
35.8. Do I have a second?
Yep.
Okay. Boom. That's all there is to it. So, one thing I will say for reaction problems, like particularly on homework assignments, it would really be great if you could summarize them sort of like this. So AX is 0, AY is 35.8 kips up, BY is 32.2 kips up. If you could sort of like do something like this. Just put them all in one spot and say, bam, there's the answer. That makes life a little easier. Didn't mean to do that, but that Y was bugging me. That was the warm-up. So let me stop for a second, see if anybody has any questions. Yes?
This is kind of unrelated, but
Sure.
I cannot find where the structural analysis notebook is on the Teams. And I
Oh,
don't know if I'm
that's-
just confused, or
Sure. No, that's fine. So, actually, let me do this. So, what you're going to do is, so if you go to the team, okay, what you're going to do is under the class notebook, okay, so open the class notebook, and then when you open that, what you'll do is right here, so under the tree, what you're looking for is content library, and it's in this folder right here.
nothing comes up. Oh, never mind. Thank you.
No, it's fine. It's fine. That is completely fine. Everybody else, I'll have that in the recording as well. So don't hesitate to ask. Please don't hesitate to ask at all. Right. Any other questions? This is good stuff. All right. So now what we're going to do is we're going to take this problem and we're going to ramp it up a little bit. Okay. And what I mean by that is this is about as easy as it gets in terms of a reactions problem. But we as engineers are going to deal with loading situations and loading parameters that are more intricate. So let's talk about some more intricate situations. First thing I want to talk about is the difference between concentrated loads and distributed loads. So that previous example employed concentrated loads, also called point loads. And so what I mean by that is I have 20 kips sort of lumped at one point, 30 kips lumped at one point, 18 kips lumped at one point. There are real-world physical examples of that. A very common example of where point loads come in the real world is framing connections. So, for example, if you look at a floor system, you will have these floor beams framing into these larger girders, right? And the girder, so here's the girder, and there's floor beams framing in every so many points. And so the reactions from those floor beams we treat as point loads on that girder. So that's a very real example of where we would see that in reality. But loads can also be modeled distributed. In other words, instead of lumping it all at one point, we spread it out over a given area or spread it out maybe over the length of the beam. Now, here's an example of what I mean by that. So let's say we were designing or looking at, like a ballroom facility. In no way, shape, or form would we analyze this and treat every person as a point load. No way. That'd be nuts. Instead, what we do is we look at what this structure is being utilized for, and we develop a pressure load, let's say, to apply to that system. And more often than not, we don't need to come up with those loads ourselves. There are guides and references that we can use. So, for example, one of the most commonly referenced documents in engineering, period, is ASCE 7. ASCE 7 is a document which, it's like yay thick, and all it does is detail minimum design loads for buildings and other structures. So it will detail what is the snow load you should be using in Huntington, West Virginia, or how much wind should you be designing a building for depending upon how tall it is, or what's its exposure category and all that stuff. And it will also list out occupancy loadings for what the building is used for, right? So a ballroom is going to have a live load. A library is going to have a live load. An ice skating rink is going to have a live load, and so on and so forth. So we as engineers don't need to come up with that more often than not. We can look that up. Now, what that looks like from a structural perspective is imagine this area right here. This is the ballroom. Okay, so this, what is this? This EF L, K, like this whole area, that's the ballroom, okay? And so we assume that that ballroom has a pressure load on it. Let's call it 100 PSF. So that's 100 PSF applied over the entirety of the ballroom. Now, under the ballroom are a series of floor beams that are supporting the ballroom up in the air, because that ballroom might be on the second or third story of a hotel complex or whatnot. So what we would do, and we'll talk about tributary area later, but we would use the concept of tributary area to take this pressure load and distribute it to each of the floor beams. So if we're looking at the floor beams, we don't see a point load, we see a spread out distributed load. So instead of 20 kips, maybe it's 2 kips per foot or 3 kips per foot, etc. So this is a very, very common means of developing structural models. This is also the way that we handle self-weight. Every beam, I don't care what it is, must be strong enough to withstand its own self-weight. And self-weight is more often than not modeled in a pounds per foot type scenario. Now, here I go making things complicated. In addition to uniformly distributed loads, so this is a uniformly distributed load, this will just be a constant load, we are also going to deal with triangular loads. Okay, so we are going to deal with loads that look something like this. So like from B to the end of this beam, we go from 0 to 3 kips per foot, linearly distributed. And I'm sure some of you are thinking, oh, come on. We don't see that in the real world. Yes, we do. I'm going to give you 2 examples of where we see triangular load distributions in the real world that directly applies to civil engineers. The first is hydrostatic effects. So this is either water or earth pressure on a dam. As you decrease in depth, the load increases, and so you have a triangular distribution of force on that dam. That is how we deal with hydrostatic forces, is a distribution such as this. Another example that is very more directly aligned with structural engineering is what happens to snow. Okay, so particularly snow drifts. So what happens is snow lands on the roof. Okay, and then wind comes. I mean, usually snowstorms have some wind associated with it, and that wind causes the snow to collect and sort of bunch up onto a given part of the roof. Have you ever been on top of a commercial roof, like a roof of a building, something like this? Has anybody ever been on a roof like this? Is it like that? Or is it actually kind of flat? They're pretty flat. Now, there is a little bit of slope to it for drainage and things like that, but more often than not, they're pretty flat. Okay, they're pretty flat, and they usually have a little curtain wall, about, I don't know, yay high, something like that, right? So, snow falls down, snow's collected on the roof, and then the wind blows. Now, imagine that little curtain wall about like this. As the wind blows, the snow is going to bunch up along that wall, and you get this sort of like triangular distribution of snow, and we call that snowdrift, okay? When we analyze a beam that in a roof system under snow loads, there are load cases where we have to apply the snow load as a triangular load to account for that snowdrift. And depending upon the geometry, it might actually govern your design. So, do we deal with triangular loads? Yes. We actually deal with them in real life. So, my general philosophy when I teach a class like this, I really try and ensure that if I show you something, it's something that relates to what you'll see in the real world. So, I like theory. I think theory's great, but it's got to have a real-world application. Okay. Now, when we deal with distributed loads, an easy way of dealing with it is to idealize it as a concentrated load, right? So, for example, if I have a uniformly distributed load, let's say it's L long, and it's a magnitude of W, like 2 kips per foot could be W, and L could be 10 foot, what have you. What I will do is I will collapse that into a single point load. The magnitude of that load, an easy way of thinking about how much that load is to just collapse it into whatever the area is. So this length times this height, that's the magnitude of the force. But I collapsed it into a point load. Where do I put it? I put it wherever the centroid is. Okay? So for a rectangular distribution, the centroid is right smack dab in the middle. L over 2, L over 2. But what about a triangular distribution? Remember, if you have the right triangle, the centroid of a triangle is a third of the way over. Y'all remember that? So if I have a triangular distribution, so I take the area, W times L over 2, and then I place that concentrated force effect a third of the way from the big end of the triangle. Okay? Now, this note over here on the right is very important, okay? What I'm saying here in this note is that this technique is just to simplify the equations of equilibrium for solving for reactions, okay? And I want to be very clear when I say this, okay? When we go later on into analysis and we're drawing shear and moment diagrams, we have to revert this back to what it really looks like in the real structure, okay? In other words, if I'm designing this table, okay, having the loads spread out over the length of the table versus having it all lumped right smack dab in the middle, those are different scenarios. That's not the same story, okay? And so I'm doing this as a means of just making the math easy, but this is what's going on in real life. So make sure that you're accounting for that when you draw shear and moment diagrams later. So that's what I mean here. V is shear in this moment. So, believe it, I know everybody here has had at least some basic experience with shear and moment diagrams. If it's been a while, we are going to really have some experience with shear and moment diagrams in here. So we will take it to the max. Okay. So far so good? All right. So let's do another example. So look what's going on here. I've taken the last example and I made it just a little more complicated. And that's how it's going to work in here. We're going to take these problems and we're just going to ratchet them up just a little bit from each problem. So, first off, this is not simply supported. Simply supported, now the supports themselves are simple. I would not refer to it as a simply supported beam because this support beam is in the middle of the beam. I would call this an overhanging beam. So an overhanging beam has simple supports, but one of them's sucked in a little bit. Let me go to the notebook here so that I have that here. Because I'll give everybody a chance to draw this out, because I know you all are diligently copying down what we copy down. Okay. Okay. So yeah, so we call this an overhanging beam, so it's going to have those same simple vertical reactions and whatnot. But I've added a few of these different loads we got to deal with. We've got triangular loads, we've got concentrated loads, we've got distributed loads. And I think you're going to find that if we had started with this example, it might be a lot. Because, we got to do this, got to do this, got to do this. But we take it slow and we ratchet it up. By the end, we're going to be doing some crazy structures. And it's not going to be any harder, really, than the very first example. It's all going to be pretty simple. Okay? All right. Okay, so while you all are writing that, let's identify some of our reactions. So I'm going to go ahead and assume vertical reactions across the board. So we'll call this By and Ay. I will say this, for some of the problems, we're going to have some problems later that are going to be really tough and to guess whether the reactions are up or down. Like right now, I think it's for the most part pretty easy, but it's going to get weird later. Like as an example, if all of these loads were over here, I would tell you AY would be acting downward. Okay, because what we would be basically seeing is sort of like a diving board, right? So imagine if you have this, it was a diving board, and you're standing over here on the very, very far end of the diving board. The back has to actually hold you hold the diving board down. Otherwise, the diving board is just going to boom. So the support at A, or the support reaction at A, if all the load was over here, would be a downward reaction, not an upward reaction. So, but the more you do this stuff, the more you start to see that. Oh, and let's not forget our AX. Okay, so far so good? Okay, now, before we start computing reactions, I kind of want to deal with these distributed loads a little bit. Now let's start off with this one over here on the right, this 1.5 kips per foot. So I have 1.5 kips per foot, and it is distributed over a length of 22 feet. I like dealing with concentrated forces. So what I'm going to do is I'm going to take that load and I'm going to collapse it into a single concentrated force. Okay? How much is that force going to be? Well, the magnitude of that force is basically going to be the area of this rectangle. Okay? What is the area of that rectangle? Here's the rectangle. It's 22 feet wide, and it's 1.5 kips per foot tall. So what is the area of that rectangle? Say it again? 33 kips. So I'm going to idealize this as 33 kips. Okay? Now, where does that go? I have to place that, a certain distance from that free end. How far away do I place it from that free end?
11 feet.
11 feet. Because this is 22 feet, it's a rectangle, so the center of a rectangle is halfway over, so I put that 11 feet over. Okay. So now, let's deal with this one. Let's deal with this right here. Let's look at this triangular load. Let's see what we can do about this. Oh. I have sort of a color scheme that I kind of stick to when I do these problems. I kind of use red for the loads, blue for the reactions, and then green for the dimensions. So,
Dr. Michael, do you want to put the 11 foot from the 4th B
but it doesn't matter. We can put both.
just to clarify?
It's going to be 11 feet from both. But yeah, we can put both. We can put both on there. In fact, we'll put both on the other one too. So let's deal with this second one. So this is 15 foot wide, and this is 2.4 kips per foot. So what's the area? Remember, it's a triangle, not a rectangle. 18. So this is 18 kips. And then from this end, what's the dimension? From this end over here on the right, or sorry, on the left. What is this dimension? 5. So that makes this 10. Okay. So one thing I will say, I genuinely try and avoid on homework and exam problems situations where the problem is confusing because the dimensions aren't clear. Like, I'd rather give you more dimensions than you need, not less. Because I can tell you that in the real world, if you're producing plans that don't have enough dimensions for a contractor to understand, they're bad plans. just my opinion. So keep it simple whenever you can. Okay. So far, so good? Okay, so first reaction I think we can solve right now is the easy one. Sum of forces in the x direction, right? So the sum of forces in the x direction tells us that AX is what? 0. That was pretty easy. I'll go ahead and tell you, next time that won't be the case. Because next time we'll start having inclined loads and inclined rollers and things like that. So that'll start to change. Excuse me. Okay. Let's deal with sum of moments. I'm going to use the same strategy. I think it's easier. Personally, I think it's easier when possible when you're summing moments to sort of sum moments as left as possible, because you're sort of starting here and working your way over. I think it's easiest that way. I mean, we can sum moments at B. There's nothing to say we can't do that. I just kind of think it's easier to sum moments at A. So I'm going to do that. And again, I'm going to do that. Okay. And so we treat this like a checklist. Do I need to deal with AX or AY? No, I don't need to worry about that. They go right through A. What about this triangular load? Does it generate moment at A? Okay. Now, we've already done the force analysis, so we know that the force is 18 kips. What side of the table does it go on, left or right? Left, and what's the moment arm? 5 feet, so 18 times 5. See, this, like, there's two ways of going about this. See, you could write it like this, or, if you wanted to do it all at once, you could say like 1/2, 15 feet, 2.4 kips per foot, and then 1/3, 15 feet. I think that's so, there's so much there. Just use the picture, use the picture, figure it out, and then now it makes it a lot easier when you're solving reactions. So I think in statics, I probably would have made you do the other way because we're learning the concept. Now, let's keep it simple. Okay, the 33 kips, does it generate moment? Or did I forget one? Don't forget that too, yeah? I'll tell you, I did that on purpose. One of the easiest things to forget is just that, forgetting something, like forgetting a load, not that, it's simple. So again, just make sure that you're going through and checking, did you account for every force and every component contributing moment? So 10 kips. How far is that from A?
22.5.
22.5. Okay. Now, what about 33 kips? How far is that?
You use 11, or is it? Or you doing it from A?
No. It's from A. We're still saying moments from A. So, what did you say?
41.
41. That's 100% right. Yes. It is contributing moment at A, and the moment arm is all the way here, 41 feet. Now, if we were summing moments at B, that'd be another story. So, all right. Now, what about BY? BY is going to contribute moment in the other direction. And what's that moment arm going to be? 30. All right. So now what we can do is say BY times 30 feet. Let's do this in steps. So somebody tell me what goes here. Like what's this times this, plus this times this, plus this times this. And that, I believe, is an 18. That is a horrible 8. I can do better. I think I did better.
For the left-hand side, I got 1,668.
1668?
Yeah.
Do I have a second on that? Yeah. Okay, and that's foot kips. Let me show you something. One of the things you'll start seeing me do, for example, is I might say 1668, and then I might do that. So this is foot kips, so like that's, your shorthand for foot, and then just like a K for kips, so foot kips. You might see me start doing that. So if you see, that's what that means. So 1668 divided by 30, I get a BY of what?
55.6.
So we'll say plus 55, and I think it's like 55.67, like it's 6 repeating, right? So. Like that, right? So far, so good? Okay, and now what we will do is sum forces in the y direction. Okay, I'm going to scroll up just a tad. I will say I'm going to do my best to try and avoid the whole like scrolling up, scrolling down, scrolling up, scrolling down, but every now and then I might need to do that. I remember when I was in grad school, I had this one professor who would like do part of the problem over here and then do part of it over here, and yeah, that was tough. Okay, so going down, we have 18, 10, and 33. And then going up, we have AY, and we have BY. But again, like last time, we know what BY is. It's 55.67. And so AY plus 55.67 kips is, okay, 18 and 10 is 28. 28, 33 is 61. Did I do that right? Okay. And so AY is positive, and it's actually a tiny number. I think it's like 5.33.
Yeah, or I got 5.4, but my calculator didn't.
And let me say this, I am really not going to get marred up in like rounding with stuff like that. Like if you're doing it correctly, you're going to get the right answer. The only thing that rounding can affect on certain problems really is when we start to draw moment diagrams, the idea is they're supposed to start at 0 and end at 0. And what might happen if you're a little off on rounding is they might start at 0 and end at 0.1 or negative 0.1. That's not a big deal. Don't let that worry. But just know that something like that can happen. So, and there you go. What do you think? It's not too bad, right? We're slowly but surely getting there. Just shaking off the rust a little bit. I'm sure you probably, it's been a while, I know. What do you I'm just curious. And to be clear, I'm not a micromanager. I'm sure there's people in here who say, I'm not using the table, I just want to write the equation. That's fine, I don't care. This table,
I dig the
you like the table?
I dig
Table's
the
good
table,
stuff.
yeah.
Table's good
I was
stuff.
on the table earlier.
Yeah, what? That's kind of. I was like, why did we get the table lesson?
Because of following semesters.
It's something new. Keep us excited, right?
No, you're just full of surprises, aren't you? Do I strike you as a guy that's full of surprises? I come in and I have my lecture notes prepared 3 weeks in advance. Yeah, I'm full of surprises.
You always have to be.
What's that?
You always have
I
to
know I'm a victim of the routine. That's for sure. So, it's so clear.
You don't remember the fun times with that?
Oh, I remember the fun times. I remember them quite well. So, any questions? So I've got 2 problems for your homework. I think it's either 5-6 and 5-12 or 5-5 and 5-12. I can't remember. One of them is 5-12. No, sorry, 3-12. Last time, 3-12. 3-6 and 3-12 or 3-5 and 3-12. I can't remember. But if you get this, you shouldn't have a problem. They are pretty straightforward. One thing I will tell you, I think that it's either this assignment or the next one, but one of them has a beam that has some variable change in geometry, like the actual beam looks like it gets deeper or shallower along the span. That doesn't matter for the purposes of computing reactions. It will affect things like computing deflections, but for this, it doesn't affect it. As long as your structure is statically determinate, the beam could be steel, concrete, popsicle sticks, it wouldn't matter, and you get the same reaction. So far so good? I'm giving you 5 minutes of your life back. You have a wonderful weekend. I will see you all on Monday.
Could you go ahead and post the pictures for those